Okay, so this is the first lesson that goes with section 11.5, which is lines and planes in space. And we're going to spend 3 separate lessons going over these things because there's a lot of stuff going on here, and a lot of things in Calc 3 have to do with finding tangent planes to surfaces and lines that are the curve of intersection of surfaces and things like that. So we're going to spend a little bit of time and slow down a bit on this section and really split it up into 3 quite different but quite complicated lessons in their own right. So this first lesson, I'm going to focus on just lines in space, all right? So if you have a line in space, a line L parallel to the vector V, whose components are ABC, that passes through a point P, x1, y1, z1, is represented by parametric equations. So first things first, that's important, is when you have a line in space, it has parametric equations. It's not one equation, it's 3 equations, all dependent upon t. All right, so when you have a line in space, it has 3 parametric equations, and the easiest way to get those equations is you need the vector indicating the direction of that line and a point that's on that line. Then the vector becomes your coefficients for A, B, and C, and the point just becomes your, the point just becomes your constant in each of those terms. Okay? So basically the t comes from the direction vector of the line, and the constants represent the 3 coordinates of any point on the line. This is also important. The t comes from the direction vector. When we talk about planes, it actually doesn't come from a direction vector, so that's important to remember. A line, you need to know its direction. That vector gives you the coefficients. What you also have is 3 coordinates of any point on the line. That means if you used one point, you get one equation. If you use a different point, you get a different equation. And we'll talk about that right now. Find 2 sets of parametric equations of the line pointing in the direction of this vector, 2, -3, 4, and passing through that point. So we're supposed to find 2 sets. We'll probably find 3, but 2 is in the directions here. So if I have a certain vector and a certain point, I can very easily make a line, and that line is x equals 2t plus 1, y equals -3t plus 5, z equals 4t minus 9. And if you look, it seems really obvious how all that stuff happened here. 2, 2t, -3, -3t, 4, 4t, 1, 5, -9, 1, 5, -9. Done. There's your first set of parametric equations. Now what if I wanted a second set? Well, the second set just says this needs to be the direction vector, but it doesn't say anything about the magnitude of that vector. So technically, I could take this direction vector, multiply it by any constant c that I want, and make those the coefficients. So I could make it x equals 4t plus 1, y equals -6t plus 5, z equals 8t minus 9, and these are the exact same line. The other thing we can do with it is say, well, if it has to pass through this point, but I know it goes in this direction, I can use those 2 things together. So if it passes through this point and goes in that direction, that means x increases by 2 when y increases by -3, when z increases by 4. So if 1, 5, 9 is on the line, then so is 3, 2, -5. I increased x by 2. I decreased y by 3. I increased z by 4. So I could now use this as my initial point and make it x equals 2t plus 3, y equals -3t plus 2, and z equals 4t minus 5. All 3 of these equations right here are the exact same line. It's just different ways to write it, okay? All right, so find a set of parametric equations for the line passing through these 2 points. So what we've learned is to get the parametric equations for a line in space, you need a vector that indicates direction, and you need any point on that line. Well, I have 2 points on that line, which means I can use them to get a vector and use one of them to get my initial point. So very quickly here, my vector that indicates direction is going to be 0, -9, -3. So 0, -9, -3. Or, because if I don't want to use negatives, I can call it 0, 9, 3, same direction. And so I can have x equals 0t minus 3, y equals 9t plus 0, z equals 3t plus 8. There's one set of parametrics. Now, if I want the symmetric equations of a line, there's two different ways to write a line. I have to be honest with you, most of the time you're going to want it in parametric form. So that form that I've been showing you with the x equals, y equals, and z equals, that's primarily what we're going to use. However, you can also do something with the symmetric equations of a line, and basically all you do is you take these equations up here, you take these guys up here, and you solve for t. So t equals x minus x1 over a, x minus x1 over a, y minus y1 over b, z minus z1 over c. This t equals is in parentheses because we don't actually write that, we just write it like this. The benefit to that is it's kind of one extended equation. The fallback from that is most of the times we really want things in x equals form. So you just have to kind of play it by ear and see what's been asked of you and what you need to do with it to determine the form that's appropriate. I will be very specific and say parametric or symmetric. That's usually what you're going to look for. But again, if you see something and you feel like you need one form over the other, use that other form. So what we want to do is create symmetric equations for the two examples above. So I have one example there. I have the other example right here. I just took a snapshot. You can obviously just look up. So if I want to create these equations, again, symmetric equations are basically when you solve for t. So if I take this first equation and solve for t, it's going to be x minus 3 over 2. I take the second equation and solve for t. I'm going to have y minus 2 over negative 3. I take the third one. I'm going to have z plus 5 over 4. If I want symmetric equations for this one, I have to solve for t, but I can't because there's no t in this first one. Basically what we do when that happens is we just rewrite the equation, put a comma, and then solve whatever else can be solved for t down here. So here I've got y equals 9t, so that's going to be y divided by 9. And here I would have z minus 8 over 3. So this would be the symmetric equation. Even though technically it's two equations, we call it the symmetric equations for it. Find symmetric equations for the line passing through the point 2, 3, 4 and perpendicular to both of these two vectors. All right, well, the first thing I can do is this perpendicularity piece. When you're in parametric form, we really want to know this direction vector, right? And it goes in front of the t. So when you're in symmetric form, we're going to find our direction vector and put it on the bottom. So if I need to be perpendicular to two vectors, how do I find a vector perpendicular to two vectors? I know, I use a cross product. So I'm going to do a cross product here, and I'm going to call it V cross W, and that's going to be I, J, K, negative 2, 4, 6, 1, 5, negative 2. And I is going to be multiplied by negative 8, take away 30, which is negative 38. J is going to be multiplied by 4, take away 6, which is negative 2. And K is negative 10, take away 4 is negative 14. So this is going to be negative 38, 2, negative 14. So there's my direction vector, and there's a point. So if I write the symmetric equations of a line, I'm going to do x minus 2 over negative 38 equals y minus 3 over 2. And I can shift this, here we go. And then equals z minus 4 over negative 14. And that would be my symmetric equation. So in parametric, your coefficients are your direction vectors. In symmetric, your direction vector is your divisor. In parametric, you add the initial point. In symmetric, you subtract the initial point. Okay, so what do we got next here? It's hiding on me. Okay, so next, determining if I have two lines that are parallel, coinciding, and intersecting, or skew. Now, if you were in my class right now, I'd be holding up a bunch of pens and yardsticks and stuff and trying to figure this out. So I'm going to try to do the best I can on this video screen. But hopefully this will work out for you. So parallel lines. Parallel lines look like that. They are two lines in the same plane that never intersect. Okay? Skew lines, on the other hand, would be something like this, where I have a line like this, and then I have another line like that, but they lie in parallel planes. So this is in one plane, that's in another plane below it. Imagine two pieces of paper hovering over one another. You draw a line on one, you draw a line on another. Those would be skew lines. They're never going to touch, but they're definitely not parallel because they have different directions. Coinciding would be like a line like this, and then another line like this. Basically, they have the same direction vector or parallel direction vectors, and they have different initial points. Okay? And intersecting is exactly what you think it is. They look like that. They're in the same plane, and they cross themselves. Okay? So, how do I figure out the difference? All right, well, coinciding. Two lines are coinciding if their direction vectors are parallel, and the vector connecting their initial points is parallel to that direction vector. Let me quick show you a demonstration here. This is one line. This is another line that's coinciding with it. You can agree that just by looking at these, the direction vectors are the same. Now, let's take their initial points and connect those. Is that vector parallel to the direction vector? Absolutely. Now, why does that make these coinciding and say not parallel? Because parallel lines would have the same direction vector. Here's two parallel lines. Their direction vectors are obviously parallel, but the vector there that's connecting their initial points is not parallel to that direction vector because it's kind of one hovering over the other. Okay, so coinciding. Two lines are coinciding if their direction vectors are parallel and the vector connecting their initial points is parallel to that direction vector. So, show that this line is coinciding with that line. So our direction vectors are going to be v equals 3, 2, 1. We'll call the other one w equals -6, -4, -2. How did I get that so fast? I looked at the coefficients of t. Now, is v parallel to w? Yes, v is parallel to w because v equals, what's that going to be, -1/2 of w? So they are parallel vectors. Now I need to find the vector connecting their initial points. So their initial points are -5, 0, 6 and 4, 6, 9. So the vector connecting those, I'll call it the vector p, is going to be 9, 6, 3. Well, let's see. P would be parallel to v if p is 3 times v. 3 times 3 is 9, 3 times 2 is 6, 3 times 1 is 3. Yes. So these are coinciding because of all the reasons I just talked about. Parallel direction vectors, and a vector connecting their initial points is parallel to the direction vectors themselves. All right, so parallel lines. Two lines are parallel if their direction vectors are parallel, and they don't coincide. All right, so write the equation of a line that passes through this point that is parallel to this line. All right, well, first I should probably make sure that this point isn't on this line. So let's see, when x equals -4, t would have to be -4/3. And when t is a -4/3 here, this absolutely won't equal 5. So these are definitely not going to be the same line. Now I just need to write a parallel line. So I'm going to have x equals y equals z equals. They should have the same coefficients for t, 3t, 2t, 3t, and a different initial point, -4, +5, 0. All right, and last but not least, I have intersecting versus skew. So, two lines are intersecting if their direction vectors are not parallel, and a point of intersection can be found. Two lines are skew if their direction vectors are not parallel, and a point of intersection cannot be found. That's the easiest way to show this algebraically. So here's all the steps. Instead of reading all of these right now, because I would get bored reading them, I'm just going to explain them as I go here. So, determine whether these two lines are skew or intersecting. So it gives me only skew or intersecting as options, so I'm not going to check for parallelism here, but usually your first step would be to check those coefficients and see if maybe they're parallel to begin with. So I have these two things. Now in order to find if they're skew or intersecting, they want to be in parametric form. So I'm good here for parametric form, but this one is going to be x equals negative 2t, let's see, negative 2t plus 2, and y is going to be 3t plus 1, and z is going to be t minus 9, right? So here are my sets of equations. Now, how do I figure out if it's skew or intersecting? Well, what we do is say if they're going to intersect, the x's have to be equal at some point, and at that same point, the y's are equal and the z's are equal. So I need this to equal this at the same time that this equals that. So I need 2t minus 2 to equal negative 2t plus 2, and I need 9 minus t to equal 3t plus 1. But here's the thing. Intersecting lines are kind of like jets, where the jets have different flight paths and their jet streams cross, but the jets don't actually crash. In other words, two lines can intersect, but they can intersect at different places in time. So I'm going to come over here and call these T1 because they go with the time for line 1. And I'm going to call these T2 because they go with the line that's second. So basically what we do is we change all of these first T's to T1s, and we change all of these second T's to T2s. If you read in your book, when your book does this, it changes the second T's to S's. I don't really like that because S's look a lot like 5s to me, and I find that very confusing. So I prefer to make a little subscript. It's completely up to you what method you want. But you need to make them different variables. So I call them T sub 1 and T sub 2. Anyways, I have two equations and two unknowns, so I need to solve. In order to solve this, I'm going to multiply the second by 2 and then add. So I have negative 2 plus 18, which is 16. 2t minus 2t1 minus 2t1, that's going to cancel out. Negative 2t2 plus 6t2 is going to be 4t2, and 2 plus 2 is going to be 4. So t2, if I subtract 4 and then divide by 4, is going to be 3. And then if I substitute 3 back into one of the equations up here, I'm going to get t1 equals, let's see, negative 6 plus 2 is negative 4. So I need t1 to equal negative 1. Yes, time could be negative here, it's fine. All right, that tells me at t1 equals negative 1 and t2 equals 3, the x's and the y's for each of these two lines are the same. So let me go back and check this. So L1 at t equals negative 1, we'll call this guy L1 right here and this guy L2. So L1 at t equals negative 1, x is going to equal negative 4, y is going to equal 10, and z is going to be negative 6. L2 at t equals 3, because again t2 equaled 3, L2 at t equals 3 is going to be x equals negative 4, y equals 10, and z equals negative 6. 4, 10, negative 6, 4, 10, negative, hey, look at that, the x's, the y's, and the z's are all the same, so these intersect at negative 4, 10, negative 6. Well, Mrs. Bimber, what would it look like if they were skew? If they were skew, your x's and your y's would still match, but this would be like negative 6, and that would be 4, or something like that. Your z's would not match. Well, Mrs. Bimber, what if the x's match, but the y's and the z's don't? That means you did something wrong. Because if these two things are going to be skew or intersecting, you should be able to always find a point in time where two of the variables match and the third does not. So if you have 3 non-matching coordinates, you goofed somewhere and your t-values are wrong. Okay? So 2 that match, skew, all 3 that match, intersecting, and they intersect right there. All right, just to save a little space here, I'm going to stop this video here and pick it up where I left off in a later video, because whenever I get beyond 20 minutes, it seems to slow the videos down. So I am going to pause for now and give you a really stupid joke to go with it. So the stupid joke today is, what type of umbrella should you bring if you go on a safari? What type of umbrella should you bring if you go on a safari? An umbrella-phant.